Hello everyone, and welcome back to another video lecture. Now, as you guys remember, in the last lecture we covered the strain tensor. Now it seems only fitting that we cover the stress tensor, and in particular, the Cauchy stress tensor. Alright, so to begin, the first thing that we're going to talk about is a traction vector or a stress vector. So let's say that I have a nice bar of material, it could be steel, it could be whatever you really want it to be, and I cut it in half. All right, so I take my pair of scissors, I go snip, 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 and I'm left with two separate bars. Now, the first thing that we're going to have to try and quantify or realize is that my cutting plane matters. In this particular case, I cut just straight vertically. However, it doesn't matter if I cut vertically or at an angle, something like that, because what we're going to do is we're going to define that cutting plane with a normal vector n. So this normal vector n is actually going to be perpendicular to the surface of the cut. Now, for the next part, we're actually going to have to think back a little bit to Eng 130. Remember that if we were analyzing a beam, or in a static case, and we were to cut the beam, we release its internal forces. Well, it's actually going to be the same thing in this course. So when we cut a material, we expose those internal forces. And if we're talking about stresses, this comes in the fact that, or in the form of stresses being everywhere. So all those purple vectors there, those are all different stress vectors. Now, if we look at this, it seems a bit overwhelming. Well, what can we do to simplify it? Well, what we're going to do is we're going to define an area on this plane, which we say is delta A. And what we're going to do is we're going to take all of those internal force vectors that act on their internal stress vectors and contract them into one single vector, which is called delta F. Now, with this, we can actually define something called a traction vector, which is the stress vector at a point on a surface surrounding the point with a normal vector n, and it's basically defined as the limit as delta f divided by delta a goes to 0, or more specifically when delta a goes to 0. And we're going to talk a little bit more on how we actually calculate this, because I know when you guys look at limits, you guys say, oh, well, that's a little bit confusing. No one likes limits. Don't worry, we're going to talk about what exactly we can do with this. Now, before we get into the next slide, one thing I want to point out is that, of course, if we were to look at this, I want to say cube, but it's not really a cube, it's more of a bar. If we were to look at this bar and when we cut it, keep in mind that there are internal forces on both sides, just like back in engineering statics. Therefore, we can say that, well, if we have a traction vector on one side, well, we're going to have a traction vector on the other side. It's going to be equal in magnitude, but opposite in direction. All right, so the whole goal of this kind of lecture is to figure out what is that traction vector, or basically what are the stresses on an arbitrary plane inside of our continuum. So to do that, we're going to use our best friend, the potato. And from this potato, what we're going to do is we're going to extract a little cube of an infinitesimal dimension from this potato. So as we can see, I took a little cube here and I aligned it with our basis vectors E1, E2, and E3. Now, just like we discussed in the previous slide, each one of these faces on the cube is actually going to have a traction vector. All right, so as I can see here, I defined three traction vectors, TE1, TE2, as well as TE3, but also keep in mind that there's going to be three more traction vectors on the other side of the cube. Now, to make things a little bit easier, because of course these traction vectors are going to act in different directions, what we're going to do is we're going to simplify the traction vectors as linear combinations of the basis sets. What exactly do I mean by this? Well, if I were to look at the traction vector on this purple surface here, which I'm going to call TE3 because it is in the E3 direction, well, it's just a combination of sigma 3,1 multiplied by the vector E1 plus sigma 3,2 multiplied by the basis vector E2 plus sigma 3,3 times the basis vector E3. So it's basically the stress component acting in a certain direction. And since we have three basis vectors, keep in mind that anything that acts in a, let's say, a diagonal direction can be expressed as a linear combination. So therefore, we have a nice formula for our traction vectors where the traction vector on a surface perpendicular to a basis vector EI, well, we can calculate the traction vector as TEI is equal to sigma ij EJ. Now, this is all great if the surface we're looking for is actually perpendicular to a basis vector. If we look at this case and we went back to that purple surface here, we can see that that surface is perpendicular to the E3 and it's actually in the E1, E2 plane. So that actually makes calculations quite simplistic. Now, the thing that we're going to get into in this particular lecture, which is where Cauchy comes in, is when we start wanting to calculate these traction vectors on arbitrary surfaces. And this is where Cauchy stress tetrahedron comes on. So if we look at a tetrahedron here, it's very similar to the cube in that one side is aligned with the E1, E2, and E3 basis vectors, but instead of having a nice cube shape, we have a tetrahedron shape. So what we're going to do is we're going to analyze each one of these surfaces and apply our equilibrium equations to try and create a relationship for the traction vector on this unique tetrahedron surface in relationship to everything else that we know. So what we're going to do is we're just going to first look at each one of the surfaces and see what we know. So the first thing, look at the back surfaces. So what I'm going to do is I'm going to say, all right, I got a back surface there, which I'm going to call the green surface. And as we discussed before, since this surface is actually one of the planes created by the basis vectors, in this case E2 and E3, we know that the stresses are simply going to be sigma 1,1, sigma 1,2, and sigma 1,3, and the area of this particular triangle is just going to be denoted as A1 for now. Moving clockwise, I can have a second surface here, which I'm going to call the blue surface. And just like before, this is nice and easy because the surface is on the plane created by E1 and E2, which are basis vectors. Therefore, the stress components can be sigma 1,3, or sorry, sigma 3,1, sigma 3,2, as well as sigma 3,3, and the corresponding area is going to be A3. And then finally, that bottom surface there, again, this is in the E1, E3 plane, so therefore the stress components are very nice. It's going to be sigma 2,1, sigma 2,2, sigma 2,3, and it's going to have the corresponding area A2. So these are all the back surfaces, and again, because the planes of these surfaces are aligned with basis vectors, it's actually very easy to know the stress components. However, when we're looking at that fourth surface, the surface of the tetrahedron there, this is where things get a little bit crazy. So this surface is actually going to be defined by two things. The first one is going to be the area of the surface, which I'm going to call AN. And then the second one is the normal vector perpendicular to the surface. So remember that this surface isn't aligned with any sort of the basis vectors. Therefore, the normal vector of the surface is just simply going to be N1E1 plus N2E2 plus N3E3. Now, another thing we're going to define is the distance from basically the origin of the coordinate system all the way until the surface, and we're going to call that h. And this is going to be a little bit more important later on once we take the limit. Now, referring back to stress calculations, we know that this surface has a traction vector, Tn, just like the previous surfaces. The only problem that we have with this surface as compared to the previous surfaces is that it's not aligned with any basis vectors. Therefore, we do not know the components of Tn. So what we're going to do is we're actually going to separate Tn, here our traction vector on the surface, into three components. Tn1, so that's the component aligned with the E1 direction, Tn2, which is the component aligned with the E2 direction, and Tn3, the component aligned with the E3 direction. Why am I doing this? Well, it makes it very easy for me to take equilibrium. So we're going to go to Newton's equations of motion, which basically says the summation of the forces on this particle must equal to the mass times acceleration. So if I were to go sum of the forces in the E1 direction, all I have to do is look for any horizontal, and I'm using that of course in quotation marks, but because it's not exactly horizontal in any coordinate system, but if we were to look at it, it looks horizontal. So if I were to take the sum of the forces in the E1 direction, looking at the green surface, I see that sigma 1,1 is horizontal and it's acting left, so I'm going to go negative sigma 1,1. And remember, these are some of the forces, not the sum of the stresses. So in order to get a force, I take my stress and I multiply it by its corresponding area. So we're going to have negative sigma 1,1 multiplied by A1. Looking at the purple surface, I see sigma 2,1 is going horizontally to the left. So I'm going to go minus sigma 2,1 times A2, minus sigma 3,1 times A3 for the blue surface. And then finally, for my weird surface there, that tetrahedron surface, I don't know the components in terms of sigma, but I said that we're just going to say that it's going to be Tn1. So we're going to go plus Tn1 times An, and then finally we have to add the body forces, so m times the gravity in the horizontal direction, if you will. It makes no sense saying it, but you guys know what I'm saying. And of course, all this is going to be equal to the mass times the acceleration of this particle. Now we're going to do the exact same thing in the vertical direction. So we got negative sigma 1,2 multiplied by A1 minus sigma 2,2 times A2 minus sigma 3,2 times A3, and then plus Tn2 multiplied by An, and finally plus mg2 is equal to ma2. And then finally, we're going to do the exact same thing for that third direction in the E3 direction. Now, it's from these equations of motion that we're actually going to start determining what are those components, Tn1, Tn2, as well as Tn3. All right, so to do this, let's look at our first equation of motion. Again, it's negative sigma 1, times A1 minus sigma 2, times A2, etc., etc. Now, the first step we're going to do is we're going to divide all the sides by an. Therefore, I basically have an and the denominator of every term except for tn. So originally it was tn1 times an, but when I divide that bad boy, all I get left is tn1. But it looks like I just created a lot more work for myself because I have these an's everywhere. But there's actually a very critical relationship that's going to simplify things a lot, and that is this, where n multiplied by an is equal to a1 e1 plus a2 e2 plus a3 e3. So in summary, Ni is equal to Ai divided by An. And this comes from a nice little cross product slash triple product of the tetrahedron. So it's something we're not going to cover. It's a very I want to say disgusting proof, but proofs are nice once you get it. I was able to get it, so therefore it's a nice proof. If you're not able to get it, then it's a disgusting proof. But it makes for a good exam question, but we're not going to really go through how we got this formula. We just know that it is true. And because of this, what I can do is if I were to look at the equation above and look at the terms, I see that I have an a1 divided by an. In the second term, I have an a2 divided by an, etc., etc. So I'm going to utilize this formula to simplify what we have above. So now I have negative sigma 1 times n1 minus sigma 2 times n2 minus sigma 3 times n3 plus tn1, etc., etc. So therefore, a lot of the terms starting to look a lot more simplified, except for the last two terms on the very right. So what we're going to do to address this is we're going to look at that mass term that's in both of them. Remember that everything is mass times acceleration. In the case we have mass times gravity, and then we have mass times acceleration. So we know that mass can be determined by taking the density of an object and multiplying it by the volume it covers. So of course, we can simplify the volume since we know that our shape is in particular a tetrahedron. So we get a relationship that the mass is simply the density multiplied by an times h, all divided by 3. From there, we can actually substitute this into our equation, and we get the following, which looks a lot more gross, but it's actually very nice because now in our equation, we have two h terms. Now, what we're going to do is we're going to take the limit of this volume, or take the limit as the volume of the tetrahedron goes to 0. In other words, we're going to take the limit as that variable h goes to 0, and since we have h in those two terms, they effectively become 0. So we have basically our sum of the forces is going to be equal to 0. From here, we can see that our traction vector Tn1, or the component Tn1 of our traction vector, is simply going to be equal to sigma 1 times n1 plus sigma 2 times n2 plus sigma 3 times n3. Now, this is great. We have our first component. What about the other two components? Well, in order to get those two, all we have to do is repeat the same process we just did for the remaining two equations of motion, and we get Tn2 is equal to sigma 12 n1 plus sigma 22 n2 plus sigma 32 n3, and finally Tn3 is sigma 13 n1 plus sigma 23 n2 plus sigma 33 n3. Now this is really great because once we write all three of these equations beside each other, it's very easy to see that the relationship between the traction vector Tn and normal vector n is linear and homogeneous. Therefore, we can see that that sigma term that we have in there, that's actually going to be a tensor. More specifically, that is going to be our Cauchy stress tensor. So if I were to take those three equations and write them in the matrix form, I get the following. Now, if I were to simplify this, I can lead to the following conclusion, where my traction vector Tn on that arbitrary surface is actually going to be equal to the transpose of this stress tensor multiplied by the normal vector of the plane. All right, so if I wanted the stresses on a particular plane, all I need to do is find the normal vector of that plane and then multiply it with the transpose of the stress tensor that the object is subjected to. All right, and this stress tensor right in the center here, this is what we call the Cauchy stress tensor. Now, we're going to have a little bit of fun facts with this stress tensor, and some will be discussed later on in this video, and some will be discussed later on in a separate video. The first one, which is perhaps the most important, is the stress tensor is actually symmetric. Therefore, sigma ij is actually going to be equal to sigma ji. And we're going to discuss this and kind of prove how we do this when we start talking about momentum balance. So that is going to be a different video that will not be in this particular video. Now, another fun fact that will be in this video is that there exists a coordinate system in which this stress tensor sigma is diagonal. And we call that the principal stresses. And this goes back to our linear algebra review. Remember in linear algebra, I talked about diagonalization, saying that if a tensor is symmetric, well, then there exists a very nice coordinate system which the tensor is diagonal. And we're going to talk about that later on in this video. And another little thing that we can use this stress tensor for is calculating if a material has yielded. So a lot of you guys are familiar with the mechanics of materials. If I were to look at steel and I were to start pulling it in tension, well, we know that there's going to be a certain point at which this steel yields. Now, if I was doing a nice uniaxial test where I'm just pulling in one direction, it's very easy to tell when that happens. However, in a three-dimensional stress state, it becomes very, very difficult. So that's why we use this Cauchy stress tensor to try and figure out the relationship between the uniaxial stress state and a triaxial stress state. All right, so we're going to discuss two things before the end of the video, and the first one is normal and shear stresses. So let's say that I have my nice bar right there. It is subjected to a certain stress tensor, and then I decide, you know what, I want to cut my bar and analyze the internal stresses on two surfaces. Now, even though it is two surfaces, it's basically one surface because, of course, the traction vector in one direction is going to be the same as the traction vector in the other direction, just opposite in direction. And the normal of the two surfaces are going to be the same, just opposite in direction. So what I'm going to do is I'm going to look at the left-hand side here, and I say, all right, well, if I want my traction vector, that's simple. All I need to do is take my stress tensor that the bar was subjected to, transpose it, and then multiply it by the normal vector of this plane. Now from here, I can actually try and determine a couple other components. The first one is what we call the normal stress. So this is sigma n. So if we have our traction vector, it acts in some random direction. Now what the normal stress is, it's the stress acting perpendicular to the plane. So right here, the normal stress, sigma n, is going to be perpendicular to that surface that we cut. Now, how do we calculate this? Well, if we look at our picture here, it's just a projection. We talked a lot about this when we were doing linear algebra. This is this is why we had to do linear algebra, unfortunately, but it's to capture stuff like this. So the normal stress is the scalar projection of Tn onto the vector n. And what do you mean by scalar projection? Well, I mean I want just a number at the end. I don't want an actual vector, I just want a number. Therefore, sigma n is going to be the projection of Tn onto n. Therefore, it's going to be Tn dotted with n divided by the norm of n. So keep in mind here that this is the scalar projection. This will just return me with the magnitude of that vector. It won't return me with the vector itself. However, one little thing is nice is if we look at the norm of n, we say, oh, well, we know that n is actually a unit vector. And since n is a unit vector, the norm is just equal to 1. Therefore, we can conclude that if we want the normal stress components, remember that this is just a scalar component, all we need to do is take our traction vector Tn and dot it with our normal vector n. Nice and easy. Now, remember that we said that there's actually two components in a projection. There's that perpendicular component. However, there's also that parallel component. So this right here, which I call as tau n, or I'm just going to say Tn. It's just, oh, I guess I can't say Tn because that's the traction vector. So tau n right here, this is what we call the shear stress component. And this shear stress component is actually parallel to the surface that we cut, all right? So we have a normal stress, which is perpendicular to the surface, and then we have a shear stress, which is parallel to that surface. How do we calculate that? Well, we know that the traction vector Tn is simply the vector addition of the normal stress vector and the shear stress vector. So normally when I'm doing my nice symbols, I don't differentiate between vectors and scalars, but in this case it's kind of necessary. So what I did is for the normal stress vector and the shear stress vector, I put that little arrow sign above just to really help differentiate. Now remember that Tn is simply the summation of the normal stress vector and the shear stress vector, so I can actually rearrange it to solve for my shear stress vector because Tn, our traction vector, we already know that, and sigma n Well, we actually don't know that, but we can easily figure it out as we know the magnitude of sigma n. So since we know the magnitude of our normal stress as well as the direction it acts upon, which is in n, we can create that normal stress vector by going our magnitude sigma n multiplied by n. Now, this gives us our shear stress vector, but we actually just want the shear stress component. How do we find the magnitude or the norm of a vector? Well, we take the norm of the vector. It's pretty simple. So if I'm looking for that shear stress component that is parallel to that surface, all I need to do is take the norm of Tn minus sigma n times n. All right, nice and simple. And there's just one last thing I really want to emphasize. You guys probably already know this, but I just want to emphasize it. If we were to look at sigma n, the formulation for it, all we're doing is we're dotting our traction vector with our normal vector. And remember that this gives us a scalar value. It's a dot product. So remember that when you're looking for that normal stress component, you should get a scalar value. Same thing over on the other side. If we're looking at the shear stress here, we're taking the norm of a vector, which will result in a scalar. So make sure that you guys are getting scalars for both of these. Otherwise, something is a little bit wrong. Finally, the last thing we're going to talk about is principal stresses. So I kind of already hinted about this, but it's actually going to be very important. If you guys have ever used a finite element program before, and they give you the different options, would you like to see stress? Would you like to see strain? Would you like to see blah, 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 blah? One of the options it typically gives you is, would you like to see the principal stresses? Now, what are the principal stresses? Well, here they are. Remember that since our stress tensor is symmetric, there exists a coordinate system aligned with the eigenvectors of the stress tensor in which the stress tensor is diagonal. Therefore, it only has diagonal components, and all the non-diagonal components, aka the shear stresses, are all equal to 0. What does this look like? Well, let's say that I do my analysis. I find that these are the stresses on my cube, and I say, all right, this is great, but there exists a certain coordinate system after I rotate this in which that all those shear stresses, so sigma 2, 1, sigma 2, 3, sigma 1, 2, etc., they all disappear, and I'm simply left with normal stresses, which I call sigma 1, sigma 2, and sigma 3 in those Roman numerals sort of thing. Now remember that when we talked about diagonalization, in order for this to happen, our Q matrix has to be very specific in that the rows of Q are actually going to be the eigenvalues of that tensor. So if I were to look at the first row of Q here, this is going to be one of the eigenvectors of our stress tensor. The second row, that's going to be the second eigenvector. And finally, the third row is going to be the third eigenvector of our stress tensor. Now, what does this look like in component form? Well, let's say that I have my stress tensor sigma 1, 1, sigma 2, 1, sigma 3, 1, etc. in the original basis set. But after I transform it, so I go from sigma to sigma prime, which is Q, sigma, Q transpose, what I end up with is a diagonal matrix consisting of non-zero diagonal components. So as we see, we have sigma 1, sigma 2, and sigma 3 in the diagonals, and the non-diagonal components are all going to be 0. Now this is very special because those diagonal components, sigma 1, sigma 2, and sigma 3, those are actually the eigenvalues of our stress tensor. Now, another thing that we do is because depending on which eigenvector you use for which row, you guys are going to have different diagonal tensors. They'll all be the same, but let's say that in the first component there I had sigma 3, and in the middle I had sigma 1, and then finally at the end I had sigma 2. It's all valid. So in order to kind of differentiate this and keep some sort of consistency, what we usually do is we take the largest eigenvalue, sigma 1, and we put that in the component spot 1, 1. We take the middle eigenvalue, put that in the middle, and then we take the smallest eigenvalue and we put that in the component spot 3, 3. So hopefully that makes sense. It doesn't really matter too much. It's just to keep some sort of consistency, which always seems hard in a course like this. But yeah, that's it, guys. That's the Cauchy stress tensor. I hope you guys were able to learn a little bit at least and make your lives a little bit easier. So thank you guys so much for listening. I really appreciate it. I will see you guys in the next lecture video.